In sections 8 and 9, we want to look at some other types or classifications of reactions other than the precipitation reactions we've been looking at. Precipitation reactions are extremely common in chemistry, but they're certainly not the only kind of reaction that we have. So one type of reaction that you'll see a lot, and especially when you get to organic chemistry, these become really important, acid-base reactions. So acid-base reactions are simply reactions that form upon mixing an acid with a base. And we'll talk a little bit about what acid and base is in a minute, but for example, if we have hydrochloric acid, we looked at naming acids, so you should be familiar with that one. And this one is sodium hydroxide. This is a very common base. It is the most common base that you use in a chemistry laboratory setting. Maybe not the most common one you see outside of a lab setting, but in the general chemistry lab, this is the one. And these react to form HOH, which is H2O water, and sodium chloride. All right, so what is an acid? What is a base? An acid is a molecular compound that has a tendency to release what we call hydrogen ions, or you may hear it called hydronium ions. It looks a little different from this, but that's certainly along the same lines. So these H+ ions tend to be released when you dissolve this substance in water. Now, this is one particular definition of acid. There are several definitions of an acid that all have a little bit of variation on theme, but this is the one we're going to go with right now. It's the simplest explanation of an acid. And as you get further into general chemistry, as you get into organic chemistry, and as you get into characterizations of compounds in the lab, you'll learn some of the other definitions for acid and base. Let's just run with this one for now. What are the characteristics of an acid? Well, they tend to have a sour taste. So based on that, now again, never taste anything in the lab, but acids are something that we as human beings taste all the time. You can think of some examples of things that taste sour. Lemon juice, lime juice, any sort of citrus juice is sour because it has acid in it. If you get vinegar, if you like the taste of vinegar, that is a classic acid. That's acetic acid. If you've ever noticed that perhaps maybe your coffee tastes a little bit sour, it has sour notes, that's not a preferred profile for coffee, but the sour taste is coming from some type of acid generally. Another characteristic of an acid is that they tend to dissolve certain metals. So metals tend to corrode in the presence of acids. Now, if I have an acid, generally speaking, acid-base reaction, what is a base? A base is, again, this is the simplest definition, a molecular compound that tends to accept these H+ ions that are given off by the acid, so they do complement each other. One releases H+ ions, also known as protons. One accepts the H+ ions, or the protons. Very often, a base tends to form hydroxide ions in the process of accepting H+. Not always. The ones we're going to look at in this chapter will be producing hydroxide ions, but just be aware, again, it gets really confusing when you get into organic chemistry if you think you're supposed to have a hydroxide. So be aware, you don't always have to have a hydroxide. Characteristics of a base, they tend to have a bitter taste. Again, you're not tasting anything in the lab, but if you think about things that taste bitter to you, things like quinine, if you've ever had to take that. Certain medications have a bitter taste. They tend to be on the basic side. If you've ever accidentally gotten soap in your mouth, and notice the other characteristic is a soapy, slippery feeling. Soapiness is a characteristic of a base. Bitter taste is. And this is why you'll notice that we as human beings tend to consume a lot more acid than base. We tend to like sour taste. We know that we tend to have acidic systems, and so our bodies can accept acid. But the bitter taste are usually associated that are associated with bases tend to be associated with things called alkaloids that our bodies don't handle well. They tend to be poisons to us. So this was kind of almost an evolutionary trait. So when human beings would taste something and it would have a bitter taste, they would spit it out. It wouldn't taste good to them. Well, those bitter tastes were usually toxic plants. And so it became an adaptation for survival to not eat these bitter plants. So that's why we have an aversion to bitter taste, because these are very often compounds that are not good for us. The soapy, slippery feeling that you get with a base, again, it could just be soap, but generally speaking, it's a lessening of friction. And for some bases, such as the sodium hydroxide we mentioned, it comes not from the material itself, but it comes from the reaction of the material, the sodium hydroxide, with the amino acids in your skin, neutralizing them, and it's kind of dissolving your skin and making it slide over itself. So you need to be really careful when handling both acids and bases, but especially bases, because an acid, when it reacts on your skin, you'll know it pretty quickly. You'll feel it. It tends to itch, it tends to burn. You want to go wash that off immediately. Bases, all you feel is this really kind of neat, weird, slippery feeling until the top layers of your skin are gone. Suddenly you've got these open sores. So be very careful when handling bases. Now, Table 7.3 in your book lists some of the more common acids and bases. So we've already looked at most of the acids when we looked at naming these compounds. But the bases you may not be as familiar with. Notice these that we're looking at are all hydroxide compounds. We have sodium hydroxide, lithium hydroxide, potassium hydroxide, calcium hydroxide, and barium hydroxide. So those are all compounds that you want to be aware of. If you see a hydroxide, you're talking about a base. Now, what happens when we mix acids with bases? Acid-base reactions, as we saw earlier, tend to form water and then some other material. When we get an acid-base reaction, it's also called a neutralization reaction. And the compounds that are formed tend to be water plus an ionic compound known as a salt. Now, just to clarify, salt means a different thing to a chemist than it does to the population at large. If you were to go to anybody in the street and say, "What is salt?" they will tell you it's that stuff on the table in the shaker that you put on your food and it tastes good. There's only one kind of salt to them. I mean, maybe variations of that. You've got Himalayan salt, and you've got, the Hawaiian sea salt. You've got all these different kinds of salt, but they're all basically sodium chloride that just has other minerals in it. To a chemist, the word salt simply means one of these soluble ionic compounds that dissociates when you put it in water. Those are all salts to us. So the net ionic equation for many acid-base reactions, the salt, it's that ionic compound that's soluble in water, those are all spectator ions. So basically it's just the H plus from the acid, okay, that's coming from the acid, and then you have the OH coming from the base, and those are going to combine HOH or H2O. Okay, so you can think of this as HOH. So that's why we call it a neutralization reaction. We neutralize the acid and the base property. We make water, which is neutral, and we make salt. Now, another type of reaction that you can have in addition to precipitation and acid-base is a reaction that creates a gas. So these are known as gas evolution reactions. And these are specific to various types of compounds. So Table 7.4, shows you the types of compounds that can undergo gas evolution reactions. So sulfides are notorious for that. Sometimes there's what we call an intermediate product. Something else gets formed on the path to making the gas. For sulfides, there isn't one. Sulfides tend to react directly with hydrogen ions from water and form this H2S gas. And if you've ever been around this, you definitely know it. H2S is what's the cause of the rotten egg smell. That's the classic rotten egg gas. Smells very bad, and it's also very toxic, so not a good thing. But sulfides tend to undergo reactions to evolve gas. Carbonates and bicarbonates tend to go through an intermediate. They tend to form dihydrogen carbonate. Okay, so carbonic acid, you may also think of it that way. But carbonic acid, H2CO3, breaks down into carbon dioxide gas and water. So the gas evolved is going to be CO2 for that one. Sulfites and bisulfites tend to go through the H2SO3 intermediate and evolve SO2 gas. And then ammonium tends to break down and form ammonia gas. Okay, and I will tell you that last one is definitely one you may not think about. All of these tend to occur in nature fairly frequently, and they will occur around you. Things that you handle every day contain these compounds and may evolve some of this gas. But the ammonium one is one that may happen when you least expect it. I found that one out the hard way. Actually gassed myself one day in the shower because I sometimes will mix baking soda with my shampoo. It's kind of a classic technique that you can use baking soda to clear away oils and build up in your hair. It does a good job of kind of, stripping out all the gunk, and then you can start over with clean hair. And so I thought I would save myself a little bit of time. I would mix the baking soda, the sodium bicarbonate, with my shampoo, which I had done on numerous occasions, and it worked fine, saved me some time. Well, what I didn't realize was the active ingredient in my shampoo for the detergent, the stuff that makes it foam, had been sodium lauryl sulfate. That is one particular compound that was used. Well, they had switched from the sodium lauryl sulfate to ammonium lauryl sulfate, which when you mix the ammonium lauryl sulfate compound with baking soda, it creates a reaction that releases ammonia gas. So I start washing my hair, and I notice a bit of an odd smell, and I'm like, well, that's funny. I haven't used ammonia to clean the bathroom in here lately. I don't know where the smell's coming from. And it got stronger and stronger. And then I noticed my scalp getting fairly warm, because that's a good exothermic reaction. And finally it hit me what I was doing, what had happened. And very quickly rinsed it out of my hair, checked my shampoo bottle, and sure enough, that's what it was. They had switched from sodium to ammonium compounds, and I was releasing ammonia gas. Not a pleasant thing to have happen in the shower. But anyway, so here are some examples of reactions that evolve gas. Just notice that you have something coming out as a gas in each one. I'm not going to ask you to predict these or even necessarily memorize the types of compounds that undergo, but you do need to be able, if you're given a group of reactions, be able to look at those reactions and identify what you're looking at as precipitation or acid-base, or in this case, gas evolution. So a gas is being evolved from these reactions. All right, so it does walk you through here about how to write a gas evolution reaction. And what this requires is that you recognize when you have these intermediates that decompose into gas producers and then go through to balance the equation. So it is important for you to read through this. You do have the static slide on the Blackboard site. So take a look at this one, read through it. Be sure that you understand the process they're going through, but I'm not going to ask you on a test to recreate that. You have a couple in your homework just to get familiar with them, because they are important reactions. They are things that you may need to be able to recognize, but they're not ones that we're going to, at this point, reproduce. Okay? Just be able to recognize these. Now, here's another example of why these things are important. Just a little sidebar that you have in your book talking about neutralizing excess stomach acid, classic acid-base reaction. Your stomach, normally, if all is good, contains acids, and in particular hydrochloric acid, that help with digesting your food. But sometimes you get a little bit too much of it built up. You get heartburn, you get acid stomach, acid reflux, things like that. And so what you're going to use to take care of that is something known as an antacid, an anti-acid. So you're looking for a base, something that can absorb and neutralize the stomach acid. So that's just an acid-base neutralization. Antacids tend to very often contain bases such as magnesium hydroxide, aluminum hydroxide, or sodium bicarbonate, baking soda. You'll see those very often. Or you may also see calcium-containing compounds. And those are popular as well because carbonates react with acid, okay, and they form carbon dioxide gas and water. So that can also help to neutralize acid, but you end up with a lot of carbon dioxide and you end up belching a lot. So that's where that's coming from. Interesting little sidebar there that they had. All right, and then another class of reactions that, again, you want to be able to recognize it at this point. We will do more with these reactions, hopefully later in the semester. Hopefully we'll have time to get to these. But for now, it's important to be able to recognize these. Oxidation-reduction reactions, or you may also hear them called redox reactions. Redox reactions are an incredibly important class of compounds in chemistry. This is what's responsible for the rusting on iron. Bleaching of hair. If you bleach your hair, why does that work? Or if you bleach a stain out of your clothes, that's a redox reaction. And energy, the production of electricity in batteries. If we didn't have a redox reaction, we wouldn't have batteries. Most of these redox reactions that we look at involve something reacting with oxygen. There's a lot of, oxygen-created compounds, so thus oxidation. So something is being oxidized, something is being reduced in these reactions. Now, what do we mean when we say something's being oxidized or something's being reduced? You've probably heard of things being oxidized for a long time. Okay, but what does it really mean? Well, what oxidation means is that something is losing electrons, the loss of electrons. And reduction is the gain of electrons. Okay, now I know that seems a little bit counterintuitive. We're not getting into the details of oxidation reduction right now. There's a lot more to writing those reactions and balancing them out that, again, hopefully we'll get into. It's in a much later chapter in your book. But for now, be able to recognize when you see a redox reaction, something is losing electrons, something is gaining electrons. Now, to remember the difference between oxidation and reduction, there are a couple of helpful mnemonics. Now, there's two different ones. You can pick the one you like the best. The first one is Leo the lion goes grr, where Leo, L-E-O, is loss of electrons is oxidation, and the lion says grr, gain of electrons is reduction. Okay, so losing electrons, oxidized, gaining electrons, reduced. The other mnemonic people like to use is oil rig. And this one may make a little more sense. Oxidation is the loss of electrons. Reduction is the gain of electrons. Okay. And I know it seems odd that reduction is gaining electrons. How it seems like something being reduced would be losing. This one's a little bit opposite, so that's why it's good to use those mnemonics. Leo the lion says grr, or oil rig. Oxidation, losing electrons. Reduction, gaining electrons. Now, something to keep in mind is that if you have an oxidation-reduction reaction, they must occur together. You can't have just oxidation or just reduction. That's because it's a movement of electrons. If something's going to lose electrons, those electrons can't just float around free in space. They have to go somewhere because, again, we don't like a charge on something. Things like to be neutral compounds. So if one substance is losing its electrons, something else is going to gain those electrons. Okay, for now, just be able to identify a redox reaction. You don't have to write it. You don't have to predict anything about it. Just identify it. Okay. So how do you identify it? Well, it has to meet a certain set of requirements. Okay. First of all, a substance may be reacting with elemental oxygen, so look for O2 gas somewhere in the equation. That's a tip-off that you may have a redox reaction. Look for a metal reacting with a nonmetal. Okay, so metal-nonmetal interactions. Again, just like we've been looking at what sort of ions do metals form and do nonmetals form, one gains electrons, one loses electrons. That's exactly what we're talking about, oxidation reaction, metal and nonmetal together. And then just more generally, if one substance is transferring electrons to the other. Now, you may not be able to recognize if electrons are being transferred, so what you're looking for are things that are changing charge. I have a charge on one side and a different charge on the other. So look for metals and nonmetals. Look for oxygen. Not all of these things have to be in the same redox reaction, but these are tip-offs that's what you're looking at. So if you can't classify it as anything else and you've got those, you've probably got a redox. Now there's a subcategory of redox reaction known as a combustion reaction. Now combustion reactions, we said that a redox may involve elemental oxygen. A combustion reaction always involves elemental oxygen. So you've got some sort of substance, which is a fuel, reacting with oxygen to form one or more oxygen-containing compounds, which usually includes water. A combustion reaction is going to be exothermic. It is going to get hot. And we understand that already from what we know about combustion. If you combust something, you're burning it. It's going to get hot. Okay, now here's another thing about combustion reactions. The compound that you're reacting with oxygen will contain carbon and hydrogen, or it may contain carbon, hydrogen, and oxygen. You may have a couple of other things in there, like some nitrogen or something, but it's always going to have carbon and hydrogen in it, and it's always going to form carbon dioxide and water. Okay. Now, other combustion reactions can include the reaction of carbon with oxygen to form CO2, and they may be a little bit different here. But basically, here's the upshot. You've got a fuel plus oxygen, and you're going to end up with carbon dioxide and water. Okay, and then the fuel will contain carbon and hydrogen and maybe oxygen. So something containing carbon and hydrogen and maybe some other stuff plus oxygen yields carbon dioxide and water. That is going to be a combustion reaction. That's how you recognize those. All right, so that is an overview of some of the classes of reactions that we have. In section 10, we want to look at a little bit deeper look at the classification of those categories of reactions.